Right? We're going to start now, right? So just info before I start. If you go to your Blackboard, you're going to see new file there about the tutoring and SI info. Right? You already know SI, so for the tutoring, you have one file there. You have 2 tutors this semester. Okay? So Ivan, he has been tutoring for a couple of years now. So he does all chemistry, Zen Chem and OChem, right? And then we have the new tutor this semester. So she's going to do OChem 1 and 2. Right? So if you have any question on the tutoring, you can go with this info. Yeah. Right? I just posted this morning. Alright? With that, we're gonna go to the slide over here. So we were talking about the shape of the molecules. right? So for example, hydrocarbon, methane is the simple molecule you can find, right? CH4, that is methane. So if you draw that, you're gonna draw something like this. So you're gonna have carbon, right, at the center, of course, and then you're gonna have two lines, regular normal lines, and then one gonna be the bold line there, other gonna be the dotted or dash line there, right? Do you know the meaning of that? Why you don't have the same type of line there? So why, if you write it this way, it's gonna be confusing. Of course, you have 4 bonds with the carbon. Why you have different types of lines there? So what this means is to make less confusion, to simplify the structure in 3 dimensions. So if you write this, all same line is going to be 2D, right? So you have x and y axis there, you don't have any z axis, so on there. So if you want to write the correct way, how you can do is take 2 bonds in one plane, right? So you're going to have the plane like that. Suppose this is xy plane, right? So I'm going to put these 2 bonds in one plane, like this, right? And then you're going to have one bond towards you, the viewer, and the other one away from the viewer, right? So this one towards you gonna be the bold line, right? So here, this one, the bold bond you have is this one over here, from your side, right? And then the other one, which is away from you, on the back of the pen, right? That is dotted one over here, this one. That's how we're gonna draw the 3D structure, right? Whenever you see the normal line, gonna be in one plane, and the bold line gonna be towards the viewer, and the dotted gonna be away from the viewer, right? So this is writing in 3D because the structure of the molecule is 3D. So if you connect all bonds together, they're going to be the tetrahedron, right? That's the reason why we call methane as the tetrahedral structure. That's the reason why in 3D, right? So the baseball theory going to say the structure of that. So here you're going to have all bond angle equal 109. Why? You have all 4 bond pair over here. There is no lone pair, no electrons, that does not form bond. So you have 2 electrons for this one, 2 for this one, and 2 for the other one, and 2 for the other one. So you have 4 same type of bond there. You have the equal repulsion between them. So that's going to be the most possible structure with the equal angle, right? That's the angle of tetrahedron, okay? And then the other one, so say you have the double bond. Now it is a little bit complicated. You have the chain of the carbon in which you have double bond, for example. Then what gonna look like? Gonna be something like this, right? So you're going to have the 2 carbon atoms there, and you're going to have the 2 bond in one plane, right? So that's why you have the normal line over here. So for the 2 hydrogen, you have the same type of line, right? Same for the other one. So you have these 2 in one plane, these 2 in one plane, so all are in one plane, right? So now you have the double bond. So this is from the p orbital. We're going to talk in detail in next slides. So you have the double bond out of plane, of course, but all 4 hydrogens going to be in one plane, right? Now if we talk about the shape of the molecule, So you're going to choose the center. If you choose one carbon center, then you have one bond over here, one over there, and one over there. All three are on the same plane, right? That's why it is trigonal. You have the planar after that, because all three are on the same plane. That is planar. Okay? So the angle is going to be about 120 degrees for that, right? So now you have these three bonds between the carbon. It is even complicated. Okay? You're going to look something like this. So you have the two carbon atoms there. You have hydrogen in one side, other hydrogen going to be on the other side. Right? Of course, these two are going to be on the same plane. So you have the same lines over there. Right? So these pi bonds are going to be out of plane. So I'm going to explain later. But if you talk about the atoms, all going to be in the same plane. So it is, of course, in one plane, but it is linear. You have, if you take this center, you have one line over here, the same line goes over here, right? So it is linear shape. Okay? So that's the application of Westphal theory. So in a hydrocarbon, you're going to have the carbon chains. Depending on, you have the carbon-carbon single bond, double bond, triple bond, you're going to have different shape. Okay? So a single bond, you're going to have tetrahedral shape for any carbon center. Double bond, you're going to have trigonal planar. Triple bond, you're going to have linear. Okay? So that's the shape of the molecules. So now, polarity. So I know you already know the electronegativity, right? The difference, that's going to give the polar bond. We already saw that. What about for the molecule, not for the bond? So there are two different things. So being the bond polar doesn't mean that the molecule is going to be polar all the time. So you're going to see the direction of polarity. If you have any cancellation of polarity, then even if the bond is polar, the molecule can be non-polar, right? If it doesn't cancel out, then of course the polar bond is going to make the molecule polar, right? So see example over here. So carbon, so this is the methyl derivative, right? So from methane, so you're going to have the hydrogen over here. So hydrogen there. So this is towards me, beer. So this is away from the beer, right? So now if I replace this one hydrogen with chlorine, for example. So methane was non-polar, right? Now if I replace chlorine there, now it's going to make polar bond, right? So this bond, carbon-chlorine bond you have, so this is going to be polar bond, right? This is polar. So all other are non-polar. You have only one polar bond in one direction. So what's going to be the resultant polarity? Going to be in that one direction, right? So you have one direction different than other three directions over here. So you're going to have this one, this one, this one. Those three are one kind, and then you have one different kind, right? So that's going to make the molecule polar. So you can tell that by the dipole moment value. So how you calculate that? So what charge you have between the atoms, you can call change in electronegativity for that, and then the vector direction for that. So the product of these two gonna give the value, which is dipole moment, right? So you don't need to worry about the value, but it is non-zero, right? Because you are in one direction, so it is polar. What about if I replace 2 hydrogen now? So now, still, you're going to have the polarity in one direction, and this is different than the other you have. Right? So you have unequal polarity there. They're going to make the molecule polar again. Right? So what about the 3? So you're going to have 1, 2, 3. So the resultant of that going to be in between. If you replace this one, this one, this one, what going to be the resultant? Going to be the midpoint of that. Right? So you're going to have the pull in one direction. Of course, you have different in the other direction. So not equal. Right? So that going to also make the polar. So this is also polar molecule, right? This is polar. It has polar bonds, 3 polar bonds, and the molecule is polar, right? So now the question is, what if you replace all with the chlorine? So now you have all 4 polar bonds. What is the resultant of that? 0, right? So your resultant value is 0. So this is non-polar. Or you can think this way. The pool in this side going to be cancelled out with the pool in the other side. Right? So the resultant going to be resultant pool on the central atom is 0. So it is non-polar. So that's why being polar bond doesn't mean that the molecule is going to be polar all the time. Sometimes it can be non-polar, like carbon tetrachloride. Okay? So that's the polarity thingy. So now we're going to talk a little bit about the valence bond theory. So you already know that. So the essence of that is whenever you form bond in the molecule, you're going to use the valence electrons to make that. That's the central idea. Okay? So now, you're going to have some complications with that theory when you deal with hydrocarbons. Right? So why? I'm going to show you in the next slide. So that we're going to see the hybridization for that. So we're going to cover these 2 now. Okay? So making bond between the atoms, you're going to use the valence electrons. This is obvious, right? So you're going to have the 1 electron for hydrogen. If you combine both, you're going to make the bond, right? So this is from the valence bond. So this is called the valence bond theory. Okay? So now, it's going to have limitations sometime. Right? So let's see the simple molecule, CH4, hydrocarbon. Simple hydrocarbon, right? So you already know the bond with that. So you're going to have the 2 hydrogens in one plane, and then you're going to have 1 hydrogen towards the here, and then you're going to have the 1 hydrogen away from the here. Okay? You're going to have 4 bonds there. Now, can you make this bond entirely based on the valence bond theory? Let's try to do that. Okay? So we're going to take the valence electron for the carbon. So this is core, so you don't take that. So all other are valence. So these are valence, right? So you have the valence orbitals there. Okay? So how many electrons you have in the valence cell?
4.
4, right? So you have the 4 electrons. You're going to make a bond with that. But now, since 2s orbital has a little bit less energy compared to p orbital, so 2s is going to be filled first, right? So the capacity of s orbital is 2. It is filled. So these 2 do not make any bond. right? Make bond as is, unless you do some changes. Okay? So now all pair electrons are these two. So what you can guess is you're gonna add one hydrogen with one electron over here. So we're gonna make a bond, one bond. And then you're gonna add another hydrogen here, and then you're gonna make bond over there. So essentially, if you do everything like a valence bond theory as is, the possibilities are you have one lone pair there, this one, in 2s orbital, because it doesn't form any bond, right? And then you're gonna have one bond with hydrogen there, one bond with hydrogen there. So this should be the case, right? Or if you want to add any electron donating thingy in the p orbital, say for example, if you have two hydrogen with two electron, you can make bond, one possibility, right? So even if you do that, it's not true, because you cannot have two bonds with one orbital. You have two hydrogen atoms there, right? So you have something wrong with that. So you have to do some adjustment on that, and then you can make the bond, right? So what is the adjustment? The adjustment is you're going to have two s orbital there with two electrons, and then you're going to have the p orbitals there. You have two px, two py, and then two pg, right? So you have one there. So what you're going to do is you're going to move that one electron over here, right? So you're going to move that so that you're going to have all orbitals over there. Let me write this one, 2s, and then 2p, x, 2p, y, 2pg. So now you're going to have 1, 1, 1, 1. Actually, you have 4 electrons there. We're not changing the number. We have the same valence electrons there. But now all are unpaired, singly occupied, right? And then you're going to mix after that. Okay? This is called hybridization. Mixing of them. Okay? So now you have 4 unpaired electrons, 4 hydrogens can combine there, and you can make the methane molecule. This is more viable, right? So that's the limitation of valence bond theory. So you're gonna do hybridization of that to overcome limitation. Okay? So now the question is, when you mix or when you do the hybridization, what's going to be the shape of the orbital? So at the beginning, for the p orbital, you're going to have like this, equal lobe, px, py, pg, all three going to have lobe like that. And then you're going to have the s orbital, it's gonna be spherical, right? So not circular, spherical, it is sphere. So this is the shape. If you mix these two, what's going to be the mixed orbital? So after mixing, right? So what's going to be the shape? So you have the more p character there, because you have 1, 2, 3 of them. You have px, py, pg. You have 3 of p orbitals there. You have only 1 s orbital there. So which character is going to dominate when you have the mixed orbital? Of course, p, right? So that's why you're going to have like a p-like, but a little bit of s character over there. So that's going to be the mixed one. Okay? After mixing, you're going to have the orbital like that, the hybrid orbital, right? So now, Up to this point, it is clear. So, in order to make the hydrocarbon, you have to mix the orbitals, right? So you're going to mix the p and s orbitals of the carbon. Now the question is, how many orbitals you're going to mix? That's the question. Okay? So that is the question. Do we mix all p with s orbital? Or do we mix 2 or 1 p orbital and then keep the other p unmixed? Okay? That's the question. So, how to know that? It depends on what you want to make. Okay? So, if you want to make carbon-carbon single bond there, mix all. If you have the carbon-carbon single bond molecule, which is called alkane, we're going to deal in next chapter, chapter 3, in detail, right? So you're going to mix all orbitals there, right? So when you mix all, then what's going to be the name of that? This is called sp3, going to be the name of that. Why are you going to have that? You are mixing 3 p orbitals and 1 s orbital, so it is sp3 from that, right? You are mixing px, py, pz with s orbital. So you have 3 p orbitals, 1 s orbital, it is sp3. That's how you name it, okay? So now if you want to make carbon-carbon double bond, then you don't mix all. So don't mix all in this case. Don't mix all. So you're going to mix S and PX and PY. You're going to mix these. So you're going to mix that and then keep PG unmixed. Right? So now what's going to be the name of that? sp2, right? So you are mixing 2 p orbitals with 1 s, sp2. So now if you want to make carbon-carbon triple bond over here, for example, then what are you going to do? So you're going to mix S and PX and then keep other unmixed. So keep PY and PG unmixed. So it is called SP hybridization because you have 1 P mixed with 1 S. Right? Very clear, right? Yep.
So when the bonds are being made, and say for instance this is the triple bond, so does that mean that it's bonding with the like PZ first and then going backwards like Z by X?
It doesn't matter. You're gonna make all bonds. Doesn't matter which one you start first.
Okay.
So I'm gonna show you examples. So let me see examples. All right. So now this is sp3. So I'm gonna clarify your question over here. So this is sp3 because you are making the single bond. There is no double bond here at all, right? It can be ethane, so it can be CC single bond, and then you have 3 hydrogens there, right? So doesn't matter what type of molecule you have, all gonna have the sp3 as long as all bonds are single. Okay? So now here, this is going to be the shape of the molecule. So you have sp3 orbital there, sp3 orbital over here, sp3 orbital there, sp3 orbital there. So you have a 3p mixed with 1s. So 4 orbitals are mixed together. So the result is going to be the 4 hybrid orbitals. So the number of hybrid orbitals formed is going to be equal to number of mixed orbitals. Right? So 4 participated in mixing, you're going to have 4 new orbitals, right? That's why you have 1, 2, 3, 4, right? 1, 2, 3, 4. You have 4 sp3, and then you have the bond, right? So now I'm going to come to a question. If you have this single line double, what to do? Okay? This is going to be sp2, right? So now here, you're going to have, how many mixed orbital you're going to have? You have 2p, and then you have 1s. So you're going to have 3 hybrids there, right? So 3 hybrid orbitals, right? So now I'm going to draw it to make you easier. So suppose you have 2 carbon atoms there, okay? So you have the mixed 3, so you're going to draw that first, okay? Or if I write it this way, you're going to write this too. So whatever way you're going to feel easier, you can write that way. This is px, py, pz, right? So 2px, 2py, 2b, 2z, cp2, sp2. Then what you're going to do is you're going to mix s with other. So this is sp2, 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 3 sp2. And then you're going to have the pure p, that is 2pg on mix there. Okay? So now let's make the sp2 first. Right? So now I'm going to make that. So this is 1 sp2. So this is sp2. And then I'm going to make the second sp2. Right? So this is sp2. And then I'm going to make the third sp2. So this is sp2. Alright? We're going to do for each carbon, remember. This is with the single carbon atom. Right? So those 2s and 2p orbitals are on each carbon. Remember that. Right? So now we're going to do the same for the other carbon. So you have sp2 for that. And then sp2 for that, right? And then sp2 for that. So these are all hybrid. You have 3 hybrid for one carbon, 3 hybrid for the other carbon, right? So we are done for that, right? So hybrid is done. So now what about the pure now? Okay. So let me write with this thingy over here, pure. So now pure is pure p orbital with the equal lobe. You don't have any change on that. This is 2pg, 2pg. Right? Doesn't matter whether you write p orbital first or hybrids first, right? You're going to have the same thing. So now, what you're going to do is you're going to overlap that from the side. Now it is a little bit complicated. So what you're going to do is you're going to keep these 2 hydrogen and these 2 hydrogen in one plane, right? So all these, so let's write the hydrogen there. So you have the hydrogen over here, s orbital, you have the hydrogen, s orbital, hydrogen, s orbital, and then hydrogen, s orbital, right? So you have 4 hydrogen, right? So 1, 2, 3, 4, all going to be in one plane, right? And then this one is also from the hybrid, okay? So the one towards you, out of these 2, you have 2 bonds over here, right? So this one is from the hybrid, okay? So let me write the notation, sigma, sigma. So for all hybrid, you're going to write sigma, right? So for red one, you're going to write the sigma bond. That's the notation. Bond formed from the hybrid orbitals are called sigma bond. Always. Okay? So now the question is, what about the pure P? Out of these two, the other one is from the green thingy over there. So actually what's going to happen is, so the pure P is going to be perpendicular to the flame. So half lobe going to be on this side, other half lobe going to be on this side. Okay? So same for the other carbon. Half lobe going to be in one side of the plane, other half going to be to the other side of the plane. So now you're going to have the overlap between the lobes. So you have one overlap over here, and the one overlap going to be on the back. Okay? So we called pi bond for that. Okay? So any bond formed by the pure p orbital overlap, this is called pi bond. Right? So you can say the side overlap of the pure p is pi orbital. So you have one pi orbital there, a bond there. So you have one pi bond. So this is pi and this is sigma. Okay? So whenever you see the carbon-carbon double bond, so if you have this, one gonna be sigma, the first gonna be sigma, always. And then no matter how many second bonds you have, these all gonna be the pi bond. Right? So now you can do similarly for carbon-carbon triple bond, right? So first gonna be, so if you have that, first gonna be sigma all the time, second gonna be pi, third gonna be pi. You have two pi bonds there and one sigma bond between the carbon atoms. Okay? So this holds true for all compounds. No matter what hydrocarbon you have there, if you have the carbon-carbon single bond, that's gonna be sp3. If you have the carbon-carbon double bond, that's gonna be sp2. If you have carbon-carbon triple bond, that's gonna be sp. Right? That's the notation. And if you have three bonds, the first gonna be sigma, other two gonna be pi. If you have carbon-carbon double bond, the first gonna be sigma, the second bond gonna be pi. Right? That's the notation. So how the pi bonds are formed? They are formed from the pure p orbitals only. Okay? So for the hybrid, it's gonna give sigma, the pure orbital gonna give pi. Always, all the time. Yep.
So clarify, SP3 is just one sigma.
Just sigma. If you have sp3, gonna be all sigma. There is no pi at all.
There's only hybrid and nothing pure.
Yep. So you don't have any pure orbital for sp3. You're gonna have the pure orbital only for sp2 and sp. So in those two cases, you're gonna have pi bond, right? But for sp3, there is no pi bond at all. Always sigma. All right?
Professor,
Yep.
for the SP hybridization where it's the 2 pi and the 1 sigma, are you mixing then 3s with 2px? Or
Yes, yes, of course you're going to do that. So I was just trying to escape that. Or you grab it, okay? Let me draw, okay? So you have that. So you have two hybrid, right? SP has two hybrid orbitals. You have one S, one P. So going to be two S hybrid orbitals, right? So this is one hybrid, and then this is the other hybrid. So this is SP, this is SP, right? Same for the other carbon. You're gonna have this SP, and then you're gonna have the other SP, right? So now you have the two pure orbitals for each carbon, okay? So for that, I'm gonna write with a different color. So it is 3D. It's gonna be hard to draw in 2D, but I'm gonna try this way. So this is pure 2py, for example. So I'm gonna do 2py over here, 2py, right? And then you're gonna have the one overlap between these, that's 1 pi bond lap. And then you're gonna have the another PG there, right? So I'm gonna draw this way. So this is PG, 2PG. And then I'm gonna write it this way. That's gonna be 2PG. So now you're gonna have the overlap between these two orbitals. So that's gonna make another pi. So how many pi you have? 2 pi. Right? So for the triple bond, you're gonna have 1 sigma from the sp hybrid orbitals. And then you're gonna have 2 pi from 2 pure p orbitals on each carbon. That's how you're gonna have. Good. So now you don't have any confusion between the single, double, triple hybridization. Yeah.
So are the sp hybridizations for carbon atoms only, or is it for other atoms?
It goes with the each carbon center in the molecule.
Carbon center.
Yep. You're gonna see if you have 10 carbon atoms, it doesn't mean that all carbon can be sp3 or sp2. If you have double bond, some carbons are sp2. If you have single bond, that is sp3. You can have many. All right? Yeah.
X will always be the one that corresponds to the same.
Yeah, normally you can take the first one. Doesn't matter. Px, Py, Pg have same energy. Doesn't matter who is it.
As long as, and the triple bond, as long as it's two of them.
Yeah, as long as, so question is like, can we mix like 2px with s orbital when you have sp hybridization all the time? It doesn't need to be, right? So since 2px, 2py, 2pg all gonna have the same energy, it doesn't matter whether you pick 2px for hybridization, 2py for the hybridization, or 2pg for the hybridization, right? So traditionally, just we write like s and then 2px because it is closer to that, but you can mix other. All right, so now bond, length and strength. So this table again is from your Zinkem textbook. So you have many tables over there in which you have the different value of the bond length between the atoms, and also you have the different energy for the bond. Okay? So here it is the bond length first. So methane, ethane, and ethine. So what that means is you're gonna have carbon-carbon, just simply carbon-hydrogen bond, right? So carbon-carbon, double bond, and then carbon-carbon triple bond. That's what it means, right? That's why you have sp for triple bond, sp2 for double bond, sp3 for single bond. Okay? You got a whole, if you have ethane, for example, carbon-carbon single bond. Okay? So if you compare the bond strength there, if you compare the value, what does that mean? Which bond is shorter? Triple is the shortest one if you compare it, right? So the multiple bond gonna be shorter one. This is because the nuclei gonna be tightly held together. So of course bond gonna be shorter, right? So bond strength gonna be larger for the multiple bond you have. Okay? So that's what it means. And then this S character and P character, you're gonna see these all the time in different chapters of OChem 1 and OChem 2. Right? So what is S character percentage? What is P character percentage? It depends on the hybridization, right? So if you have SP, you have the 50% S and then 50% P, right? So you're gonna have 50-50 because you have 1:1 ratio. Out of 100, 50 S and then 50 P. Out of 2, 1 S and 1 P, right? And then SP2, what's gonna be the percentage? So the total is 3. Out of 3, you have 1 S and you have 2 P out of 3. So out of 100, you're going to have 66 P and then 33 S, right? So that's how we're going to write the percentage. And SP3, you have total 4. You have 1 S out of 4, which is 25 out of 100. And then you have 3 P out of 4, that is 75 out of 100, right? So that's the percentage. So what going to be the percentage of P or S? It depends on the hybridization. You're going to see that first, find out what hybridization you have, and then you can say what percentage you have there. Okay? And then the next one going to be the molecular orbital theory. So valence bond theory had some limitations, not for the organic, but for the other, like I say, superconductivity, magnetism kind of thing, when it depends on the on-pair electron in particular orbital. So this theory actually was developed to describe that, but we're going to see orbital picture in the organic chemistry, so it's better to have some idea. Okay? So what is molecular orbital theory? So you have from here, molecular orbital. So before you make the bond with atoms, you're gonna make molecular orbital first from the atomic orbital, and then you're gonna make the bond. Okay? So what is the molecular orbital then? Of course, it is the combination of atomic orbitals, right? So what kind of combination? It is the linear combination. So additive and addition and subtraction, right? Depending on the sign or the phase of the orbital, you're gonna add them or you're gonna subtract them. So if you are confused with that, if you recall your Gen Chem, if you have the wave and you have the constructive overlap, what does that mean? You're going to add the amplitude together, right? If you are in the same page, so both are on the same page over here, if you add them, you're going to have the bigger wave with a larger amplitude, right? Same thing. So for the orbital, you're going to see the phase of that, or the direction, whether you have starting from up or starting from down, and then you're going to combine them depending on the phase. Sometimes you're going to have the constructive overlap, sometimes you're going to have the destructive overlap. So for example, if you have this wave, and then if you have this wave, if you add them, so there's going to be destructive. You have the opposite phase there, going to be cancelled out, right? So that's why, let's see hydrogen, the simple one, right? So this is hydrogen atom over here. So you have the atomic orbital, which is S there, right? You have the another hydrogen atom, which is 1s there. So now you're going to combine them. So your molecular orbital, which is sigma, that's going to be, if you have the constructive like that, you're going to simply add them, 1s plus 1s. So this is going to be like this, it's going to make the bond. So you can have the molecular orbital in which you can have the electron density between the nuclei of the atoms. That is the bonding molecular orbital. That's the name for that. Okay? If you have the destructive, if you have the opposite phase, you're going to do 1s minus 1s. You're going to take the difference of that. So when you do that, you do not have any electron between the nuclei. So no electron density. So this does not form the bond. Doesn't form bond. So if you see any star with any notation, that is the non-bonding. It does not form bond. This is from the different phase. This is just the possibilities, probabilities. Right? So those orbitals are just a mathematical representation. So in 3D, different possibilities of combination. So one gonna be the constructive possibility, other gonna be the destructive possibility. Right? If it is destructive, doesn't form bond, you don't have density between the nuclei. If it is constructive, you have that, and bond gonna be formed. Right? So if you have the double bond, same thing. So the pi gonna be the bonding, and then pi star gonna be non-bonding, anti-bonding. Okay? So this is called the molecular orbital. So let's see some examples. So for the molecular picture, so those gonna be represented like this. So all thing you see over here, so those are bonding, right? So this is sigma, you can call sigma 1, sigma 2, sigma 3, right? Sigma 3 like that. And then this is pi. So anti-bonding is not shown over here. So for all your molecular description, by default, all the orbitals shown there gonna be bonding molecular orbitals, unless it is specified. Right? If you see any pi star, sigma star, something like that, then this is the anti-bonding molecular orbitals. Other than that, by default, all gonna be the bonding molecular orbitals. All right?
Professor,
Yep.
what determines if they're going to be bonding or anti-bonding?
This is just the math,
Oh, so it's,
probabilities. So you're gonna see different possibilities of combinations. So normally when you have the excitation of electrons, those gonna come into play. But for the normal ground state, bonding molecular orbital is
and then does it have any effect on like, the atoms itself and the way they like,
of course, the stability and other things, yes. All right, so one more thing. So you do not have class on Monday, right? You know that. So we're gonna meet on Wednesday. So have a nice weekend. Long weekend, right? Thank you. Yeah, I will.